Network process presentation by team members Sankara Manoj, Sachin Subramanya Bhatt and Paya Liang. Our processor's instruction memory was designed to have an external input so that we can program the instruction memory from outside. As you can see, the debug mode is a signal that's being generated and that's being given to the instruction memory from the outside through a software register. When the debug mode is on, when the debug mode is on, we can see that the data going out to the in the pipeline is 0, so the instruction is just a no op. While we can fill the VRAM with our present instruction using instruction data, instruction address, and instruction write enable register using software registers. A register file is created using VRAM. This was done to save resources. So we technically use two VRAMs and with a common write port. So the data that's being written into VRAM is being written into the both the VRAMs, thus making them both identical. While we have a separate read data, so we can ensure that we have both register 1 and register 2 data available. A similar logic to the debug mode of instruction memory was added to the register file debug. Here we can see that when debug is on, the external write address and external write data are being written into the register file, while it is off, on the internal pipeline data is being generated. This wouldn't be an issue because when in debug mode is on, we'll be passing no ops through the pipeline anyway. So to ensure that there is no crash in the program for later. To read from the register file, we'll only be reading from register 2, and since we have made sure that we are writing the same data into both the VRAMs inside the register file, this should tell us the data in both the locations. Again, a similar logic is applied for data memory as well. Here if you can see the debug mode, when debug mode is on, all the external data is available to be written into the data memory, while the debug mode is off, the pipeline address and the pipeline data are being entered. Here as well, the output that's going into WB stage is also pulled out, and we can look at the data for debugging purposes. The instructions supported by our CPU include jump and link, branch equal, branch not equal, branch less than, load word, store word, add immediate, set less than immediate, set less than immediate, unsigned, XOR with immediate, OR with immediate, AND with immediate, logical left shift immediate, logical right shift immediate, arithmetic right shift immediate, add values into registers and store them in a destination register, subtract value from RS2, subtract the value in RS2 from RS1 and then store it in RT. Logical shift left shift RS2 by the initial 5 bits of RS1. Similarly, logical right shift RS2 by initial 5 bits of RS1. Set less than unsigned of if RS2 is less than RS1, then value of 1 is set to the destination register. XOR RS1 and RS2 are XOR and stored in the RT. And again, SRL is a logical right shift. SRA is arithmetic right shift. The difference between a logical and arithmetic right shift is the sign bit is conserved in arithmetic right shift, while it is not conserved in logical shifts. Apart from the instructions, there is a special instruction called done instruction, which is just a 32 TB1, which tells us that the processor is done and generates a signal done process for us to use that for later. This is the proposed network process architecture. So the data from the input arbiter goes into a FIFO and goes through a FIFO into a data memory and comes out. The FIFO then waits for the packet to fill up the data memory. Once the packet is filled up, it sends a signal to the core indicating that the data is ready. It also sends the addresses of the actual data, ignoring the header and tailors. So these addresses are counted by the FIFO control unit and are stored in a register file inside the core memory. The core can actually use these values to identify the payload locations and then just ignore the header and tailor data. Once the core is done, the done process signal is generated using the special instruction in our instruction set, and The done signal is sent to FIFO, which then later on moves to a next state and passes the data on to the output arbiter. Upon synthesis with Xilinx tool, the maximum operable frequency of our core is around 118.132 megahertz. The design was created and then simulated, and initially for the purpose of considering the worst case scenario, the data is in ascending order, in descending order. That is, data memory's first location is 5, then followed by 4, 3, 2, and 1. At the end of the cycle, it takes the data is shifted. That's it becomes 1, 2, 3, 4, 5. And as we can see, once the the processor is done, we get the processor done signal, and then followed by the FIFO control in the data that's going out of the FIFO. We had a few issues with the FIFOs file deploying it on the hardware, so we'll be fixing that and demonstrating that in the next video. A new script file called CoreEdge was written to interact with the core to write into the instruction memory and data memory and run the core externally. INST read comma address will actually read the in detail. It actually starts the debug mode and then gives the address that we want to read from to the instruction memory, and then fetches the data and writes it into hardware register from where we can read the value inside that address. As you can see, initially the data stored in address 0 is 0. Now let us write something into it. Instruction write has a command as a format of 0 is the address, and then we write the data. So let us assume we write dead beef, and then we read again. As you can see, the data is being written into the address location. A similar logic is applied for data memory as well. Since data memory is 64-bit, while the software and hardware registers are only 32-bit, the data is actually split into two parts: the upper data and the lower data. As we can see, initially the lower data contains beef, and then the upper data contains 0, 1. So to clear this, let's write into it. So the data write signal has 3 inputs. Command has 3 inputs. First is the address, and the next is the upper data, and the third one is the lower data. Now when we try to read from the same again, we can see that the data is overwritten. Now let us try to program a purple sort code was written in assembly, the assembly code that actually uses the instruction supported by our CPU, and a binary file was generated, making sure that there are no dependencies by inserting no ops. And this file can be used to program the core by continuously writing the instruction memory data using this functionality provided with the CoreEdge. So we'll be writing the data write functionality with 5 followed by 4, 3, 2, and 1. So we have written address 0, a value of 5 is written into address 0. The value of 4 is written into address 1. 3 in address 2. 2 in address 3. and 1 in address 4. This makes a total of 5 values. The program is written into the core file using the command write program. Upon writing the program, the program is run using the run range. And after it is run, we can validate the program using the same script. This continuously writes the addresses and reads from their locations to make sure that our data has been sorted. As we can see here, the address 0, which we have written like 0 to 4, we had values of 5, 4, 3, 2, 1, and as we can see, they have been sorted into 1, 2, 3, 4, 5. So the descending value has been sorted into an ascending value. This illustrates that our core and the functionality work. Like I mentioned, we had a few issues integrating the integrating the special network FIFO with our core, and we'll be demonstrating the results of that integration in the next video.